HVAC training. And Joel and I both have done training on just kind of general basic entry-level type training. And we decided to collaborate a little bit. And we are going to be doing this in a series. So definitely make sure you hang on towards the end of the meeting. We will be putting a link in the chat so that you can register for our next series. That'll be coming up in June. And with that, I will hand it over to Joel, our trusty National Technical Manager.
Well, good afternoon, everybody. Like Emily said, we've had opportunity to collaborate and put together a program. Now, this is very, very basic refrigeration cycle. And so thank you for joining our training today. And let's go ahead and start out with the fact that, basically, any of our champion equipment is going to be, fall within this category as far as basic refrigeration cycle, any of our HVAC or cooling equipment. But also just be aware of the fact that the basics that we're going to be talking about will cover any HVAC system. It doesn't matter what brand it is. It doesn't matter if it's a 2-ton, 5-ton, 3-ton. It doesn't matter what the SEER rating is. These basic principles will apply throughout. So let's go ahead and get started real quick. So we're going to ask that you please follow along as we discuss the refrigeration cycle of a comfort system, and really a better understanding of how a comfort system works will help us all be better at our jobs. Well, some of the key things we're going to be talking about, we're going to be talking about the compressor and heat exchangers and what they do. We're going to talk about an expansion valve and an orifice or a piston type of metering device and what it does in the refrigeration circuit. In addition, we're going to dig in a little bit deeper to the expansion valve, some of the design features. Now, we're not expecting anyone to be a mechanical engineer or anything like that, but at the same time, how does that valve work and what is it going to do to modulate, or more specifically, what's it going to do to meter that refrigerant into the evaporator coil? Then we're going to talk about the basic air conditioning cycles. We kind of pull it all. Go ahead.
Do you want to go ahead and advance to the next slide so we can see what you're talking about?
No, not yet. I'm not done introducing all that yet.
Oh, okay.
So are you at the please follow along slide, the basic refrigeration cycle?
Now we are, yes, thank you.
Oh, okay, all right. So we're also going to be talking about the basic air conditioning cycle and what that constitutes. In addition, the reversing valve and the basic operation on a heat pump. And then we'll talk briefly about the heat pump cooling cycle, as well as the heat pump heating cycle in a heat pump refrigeration circuit. Okay, so everyone should be able to see indoor coil, an outdoor coil, and a compressor at this time on this slide. Is that correct?
Mine's still on slide 2, so maybe we're just a little bit behind.
Okay.
There it goes.
Can you see that slide okay?
Yes.
Okay, so basically every refrigeration cycle or every refrigeration system is going to have, so you're going to have an coil to reject heat, and the indoor coil is going to be the cool coil. It's going to absorb heat, and we'll dig into that a little more. A compressor. So let's talk about each of these components individually. So the compressor is going to low pressure cooled into high pressure hot vapor. Now, please note it's critical that cool vapor returns back to adequate quantities to cool that motor down. Because remember, on a hermetic compressor, it's all sealed up. The only cooling that thing has is going to have that refrigerant coming back from the evaporator. Oh, you're going to have a little bit from the fan, blowing around on the outdoor unit. But basically, the majority of cooling for that motor and that compressor is going to come from the indoor coil. So we have to make sure we have the proper size suction line and the unit is properly charged. That's going to be critical. The outdoor coil is going to be designed to reject heat from that hot gas that the compressor is making. It's going to compress that refrigerant vapor into a high pressure hot gas. Now the outdoor coil is going to reject that heat, and it's going to condense that high pressure hot vapor into a high pressure warm liquid. So the condenser coil, as its name implies, is going to be condensing high pressure hot gas refrigerant is coming off the compressor into a warm liquid refrigerant. The indoor coil is going to absorb heat and boil that saturated liquid that we're going to be making. We're going to boil that saturated liquid into a low pressure cool vapor. So the indoor coil is designed to absorb heat, and this is an important concept. The indoor coil is designed to absorb heat as that as the liquid refrigerant boils off into that evaporator coil. It evaporates that liquid into a low pressure saturated vapor. And then what's going to happen, that cool vapor will then return to the compressor. And we're going to pipe this all up and get it all tied together here in a minute or two. But just wanted to make sure everybody understands there's going to be three basic components in every refrigeration circuit. You're going to have an outdoor coil, an indoor coil, and a compressor. Any questions or comments so far?
So I'll make one comment, Joel. I know a lot of people can kind of relate to like how a nice ice cold glass is on a nice hot summer day. And that could be kind of typical to an indoor coil, correct?
Yeah, that's a good observation, Emily. As a matter of fact, the indoor coil, as the air passes over that indoor coil, it's not only going to cool the air as it absorbs the heat from that air passing across that coil, but to your good point, it's also going to condense moisture out of that air. And so part of the total comfort that we're going to be feeling inside the home is going to be a result of that cool air coming off that coil, but also as it condenses that moisture out of the air, it's going to run that moisture down the drain in the form of condensate. That's why if you go outside, you'll see when your air conditioner is running, you'll see that there's water coming out of a drain line. Well, what that is, that's actually moisture that's been condensed out of the air, very much like you said, a cold glass of water condenses water or condenses moisture on the outside of that cold glass. The evaporator does the same thing. It actually pulls moisture out of the air as well as cool the air. Good question and comment. Any other good questions or comments at this time? Okay, good. So we've gone to the next slide, and let me know when you can see the slide. Okay, Emily, we have an expansion valve or TXV on the picture.
Yes.
Okay, so now, team, what we're going to be doing, we're going to be adding some components in the refrigeration cycle. Well, the next one we're going to talk a little bit about is what we call a TXV. Now, the TXV, there's several names for it. Let's go ahead and talk about some of those different names. The TXV means thermal expansion valve. There's another common name for it. It's just called expansion valve. And so anytime we're talking about a TXV or a thermal expansion valve or an expansion valve, they're all the same component. They just have different names in our industry. So what that expansion valve is going to be doing, it's going to be metering or spraying, and I want you to think about that. It's going to be spraying the liquid refrigerant into the indoor coil. It's a metering device. And so that TXV, it's going to take liquid on one side. It's going to kind of throttle in, or it's going to meter refrigerant into the cold coil. And as it does so, it'll allow that liquid refrigerant that's spraying into the indoor coil to boil off and evaporate inside of those tubes. But that metering device is very, very important, because without a metering device, you wouldn't have the ability to spray that liquid into the cold coil or into the indoor coil. So we're going to utilize a device called a TXV or an expansion valve, also called a thermal expansion valve, or we're going to be using a piston or an orifice, which we'll talk about in a minute or two. So the expansion valve is going to be located near the evaporator coil or the cold coil, and it's going to meter or spray that high pressure liquid into that coil again. Now the resulting pressure drop will turn the high pressure liquid into low pressure saturated liquid. Now please remember, anytime you have a saturated refrigerant, both liquid and vapor are present together. And so as we spray that liquid into the coil, it's going to start absorbing heat as it boils off into a vapor in the indoor coil or the cold coil. But that's what the metering device does. It sprays that liquid in to the cold coil. Let's take a look at that expansion valve. And Emily, can you see the expansion valve slide okay?
I can.
Okay, so the expansion valve, we're not going to get really super technical here, but there are some components within that valve that kind of help explain how it works. You'll notice on the left-hand side of the picture there, where it says liquid line, we're going to have liquid refrigerant, that's coming from the condenser. We're going to have that liquid refrigerant going into this valve assembly, and it's going to be going past a seat and a valve. Now, what's going to happen, there's going to be a spring that's going to try to close that valve off, as you can kind of look at the graphic there. And in addition, on the top of that valve, there's going to be a diaphragm assembly. And that diaphragm assembly is going to be hooked up to a sensing bulb. You'll see that sensing bulb at the outlet of the evaporator coil. So what happens is the valve is going to be sitting here opening and closing based on the temperature of that sensing bulb at the outlet of the coil and based on the pressure on top of that diaphragm. So the whole idea behind this expansion valve, it's an automatic metering device. Let me say that again. It's designed to be automatically spraying refrigerant into that evaporator coil based on how much refrigerant it needs inside that coil. Now, we're going to be talking about a piston or an orifice and how it's going to be different here in a minute or two. But the expansion valve is a mechanical device that's going to be looking at sensing bulb pressure and temperature at the outlet of the evaporator and pushing against that spring. So basically, as the evaporator gets hotter, the sensing bulb is going to get warmer. It's going to put more pressure on top of that diaphragm, which is going to drive that valve open. When we drive that valve open, we're going to allow more liquid to go into that valve and more liquid to spray into the evaporator. When that happens, it's going to start cooling the evaporator down. You get the idea. So the expansion valve is designed to meter refrigerant into the evaporator coil at the proper amount so that that evaporator is going to be working at optimal conditions. And so an expansion valve will always give you, this is the important part of this lesson, an expansion valve will always give you better refrigerant control than just a piston. Any questions or comments on that concept of how that expansion valve is opening and closing to provide the optimal refrigerant flow into that evaporator coil? Any questions on that? Everybody good? Another type of metering device that's going to spray liquid refrigerant into the evaporator coil is what we call a piston or an orifice. Now, you'll notice that on the left-hand side of the picture or the graphic here on the PowerPoint, we have a liquid line adapter where liquid's going to be coming in from the condenser coil, and it's going to be going through that orifice or that piston into the distributor body, which is going to be spraying that refrigerant into the evaporator coil on the right-hand side of the screen. Now, a piston or an orifice is nothing but a hunk of brass or a piece of brass with a hole drilled in it. So there's no real throttling or metering going on other than the size of that hole. So based on the size of that hole, what we call the orifice size will determine how much refrigerant is going to be sprayed into that evaporator. And logic will tell us that a smaller unit will have a smaller hole because we need less refrigerant in there, like on a 2-ton unit. And a larger hole, very bigger piece of equipment, like a 5-ton unit, for instance. So the orifice is going to be a fixed metering device, what we call a fixed metering device, and the fact that it doesn't throttle open and close like the expansion valve does. It's just a hole, it's just a hunk of brass with a hole in it. And so based on the amount of pressure that the liquid is coming up to that hole or that metering device will determine how much refrigerant you're going to spray inside of that evaporator coil. But it does the same thing. It just sprays refrigerant into the evaporator coil. But we need to remember a fixed orifice is very, very simple. It's very, very reliable, but it's not going to be near as efficient as an expansion valve because the expansion valve is going to be constantly modulating and providing the optimal amount of refrigerant flow into that coil. The fixed orifice is just a hunk of brass with a hole in it. And so it's gonna be fixed, and there's no adjustment to it. Any questions or comments on those two types of metering devices before we continue?
Joel, on the history, we've always had both of those, but was one of those more recent than the other?
That's a pretty good question, Emily. Yeah, it seems like recently, and I say recently, in the last 5 or 10 years, most manufacturers, us included, have gone away from a piston or an orifice metering device because they're not as efficient. And so for optimal SEER rating and for optimal efficiency ratings and stuff like that, an expansion valve is just a better metering device because it gives you better refrigerant control. but the piston is very, very reliable. So, you don't have any moving parts on a piston. And so it's kind of a toss up from an engineering standpoint, which is going to be better and what's the application. But an expansion valve is a superior metering device. So even though it costs more, it's going to give you better control and better comfort and overall better efficiency because you can modulate that refrigerant into the coil with an expansion valve where you can't with an orifice. Good question. Any other good questions or comments?
I see Chris has asked, can a TXV be installed, let's see, on both AC and heat pump?
That's a very, very good question. Yes. So all of our expansion valves that we provide on our Champion equipment and our Champion coils are going to be heat pump compatible. Now, what I mean by that, it's going to work well on an AC unit, but it'll also work well on a heat pump as well. And we're going to learn here in a little while why that has to be what we call a biflow TXV. We'll learn about that in our heat pump module here in a few minutes, but the answer is yes.
And to comment further on that, currently our only piston option is on our 13 SEER entry level AC unit. If we're doing a heat pump, our matches do require the TXV.
That's excellent. That's an excellent observation. That is correct. So the only product we currently have anymore that's rated with a piston is our straight cool 13 SEER product that we can sell in the northern regions, but everything else in our Champion lineup is going to be rated with an expansion valve. Good comment. Any other good questions or comments at this time? Okay. Emily, we make sure we can see this slide. So what we've done on this slide, team, is we've just incorporated a piston in our piston or an orifice in the refrigeration circuit, but it goes in the same place that the expansion valve does, and its function is to spray refrigerant. Again, that orifice is located near the evaporator, and it's going to spray that high pressure liquid into the coil and meter that refrigerant into that coil. So like an expansion valve, it'll be in the same physical location, but it'll just be a fixed orifice instead of an expansion valve in our example. Any questions on that? Okay, we'll go to the next slide. Can everyone see this slide okay? Basic refrigeration cycle.
We haven't quite got there yet.
Okay, no problem.
We're there now. Thank you.
All right, team, well, let's pipe this all together. So we have an outdoor coil we've learned about. We've got an outdoor coil. We have an indoor coil. We have a compressor. We have some sort of metering device. Let's pipe this all together now and start looking at some of the key things that's actually going on. So from the compressor, we're going to have a hot gas line from the compressor going to the outdoor coil. And as that hot gas goes into that condenser coil, as that hot gas passes through that condenser coil, that outdoor coil is going to reject that heat from that hot gas and turn that high pressure hot gas refrigerant vapor into a liquid. That liquid refrigerant will then pass through a filter dryer to the expansion valve in our graphic. The expansion valve at that point will spray that liquid refrigerant into the evaporator coil. We're going to get a pressure drop, but we're also going to start boiling that liquid refrigerant off inside the coil. Now, let me pause for just a second. When we think about something boiling, we think about, hot water and about 212 degrees and all that stuff. Well, I want everybody to kind of shift their way of thinking a little bit. Refrigerant is a specialized chemical that boils at a very low temperature. As a matter of fact, if you had Superman eyeballs and you took some refrigerant and you actually looked inside of a coil or you actually looked inside of that evaporator, you would notice that refrigerant, that specialized chemical that we call refrigerant, is actually boiling at about 40 degrees inside of that coil. If you were to take that same, for instance, 410A refrigerant, 410A, and you were to take a Pyrex cup and insulate it and pour some 410A into a Pyrex cup and at just atmospheric pressure, sitting on a kitchen table, and stuck a thermometer in there, you would find that refrigerant is actually going to be about 60 degrees below zero. So these refrigerants, they're actually specialized chemicals that boil at a very low temperature. So in a refrigeration circuit, when I talk about we're spraying that refrigerant into the evaporator and it's boiling off. You got to remember, at typical evaporator pressures that we see in the cooling cycle, at typical evaporator pressures, we're saying it's going to be at about 40 degrees Fahrenheit. So we're actually boiling that refrigerant in the evaporator at about 40 degrees Fahrenheit. So please keep that in perspective when we're talking about boiling refrigerant, because it is a specialized chemical. It isn't like water. It actually boils at a very low temperature. So kind of be thinking about that. So as we boil that refrigerant in the evaporator, we're going to change it into a cool vapor. And that cool vapor will then go back to the compressor on the suction line. And remember, that cool vapor is going to cool that compressor too. So that suction line size and the length of that suction line is very, very important. And now let's go ahead and activate the screen a little bit, and we can kind of see how the refrigerant's flowing through the refrigeration cycle. As we talked about it, the compressor compresses that hot gas, goes to the condenser, down the liquid line, past the expansion valve, through the evaporator coil, back on the suction line, and now the complete air conditioning cycle is complete as you kind of see the arrows pumping, and you kind of can visualize how that refrigerant is moving through the refrigeration cycle. Any questions or comments on that? Everybody good? Okay. Let's talk about it. And again, I want to remind everybody, it doesn't matter if it's a piston or an orifice as a metering device, or if it's an expansion valve. The refrigeration stays hot gas from the compressor, goes to the condenser, which turns it into a liquid. The liquid goes down and hits a metering device. It sprays it into the evaporator. Then that cool suction gas goes back on the suction line, back to the compressor. So it doesn't matter the type of metering device we have, the refrigeration cycle stays the same. Okay, any questions on the basic refrigeration cycle and air conditioning before we look at some other subjects this afternoon? Everybody good? Emily, is the screen looking okay?
Oh, sorry, I was talking. I forgot to put it on mute. But yes, we are an orifice and piston visual right now.
Got it. Okay, sounds good. All right, team. So let's talk a little bit about the difference between an air conditioning system and a heat pump. The main thing is what we call the reversing valve. The reversing valve is going to be in the outdoor unit, typically near the compressor. And the hot gas line is going to be, we're going to notice that there's going to be a hot gas line coming into the reversing valve, and it's going to be the single line by itself in the middle of the three. And then in the compressor suction line, you'll notice that you'll have a hot gas line by itself. Then you'll have three other lines. You'll have three other lines on the compressor. Three other lines on the reversing valve, and the middle of the three will be the compressor suction line. So the reversing valve, it's designed to actually divert hot gas either outside or inside based on what mode of operation we're in. And we're going to talk a little bit about that, but we just kind of wanted to show you a little graphic of a reversing valve before we get into that gas flow here in just a moment. So Emily, we should be able to see a graphic of a reversing valve in cooling and heating mode of operation. Is that correct?
That is correct.
Okay, so team, you'll notice I've made a little bit of a graphic here. So let's just talk about that reversing valve for a second. So in the cooling mode of operation, remember that single line by itself is going to be the hot gas line from the compressor. And we're going to tie this all into a refrigeration circuit here in a few minutes, but I just want to talk about that valve by itself individually. So in the cooling mode of operation, we notice as we take a look at this graphic that hot gas goes to the outdoor coil, where it's going to be condensed into a liquid like we talked about before. On the indoor coil, that cool gas coming back on that suction line from the indoor coil in the cooling mode is going to come and it's going to loop through. It's going to loop through the reversing valve and back to the compressor. So the reversing valve in the cooling mode of operation is going to look a lot like what we just talked about in an air conditioning cycle. Hot gas will go to the outdoor coil, cool gas will come back from the indoor coil and goes back to the compressor on the suction line. But now hang on a second. When we go in the heating mode of operation, When we go to the heating mode of operation, we're going to switch that reversing valve, and we're going to now take hot gas from the compressor, and we're going to divert it to the indoor coil. I want you to catch that. We're going to divert hot gas to the indoor coil in the heating mode, which makes perfect sense because now we're going to be using the refrigeration circuit to heat the home as well on a heat pump. So the indoor coil, on a heat pump becomes the condenser coil in the heating mode. Let me say that one more time. In the heating mode of operation, the indoor coil on a heat pump becomes the condenser. We're going to take hot gas and go to the indoor coil. We're going to condense that hot gas into a liquid on the indoor coil and push that heat into the house where we want it in the heating mode. And then the outdoor coil is going to become the evaporator, which makes sense now because the outdoor coil in the heating mode is going to absorb heat from the atmosphere and then return that cool gas back to the compressor. So in the heating mode of operation, we're actually going to switch modes from cooling to heating by way of that reversing valve. Any questions or comments on that idea so far? Excuse me. Okay, the next operation. Emily, can you see the heat pump cooling operation screen?
We are following along. Yes, we can.
Fantastic. So we see there's more components in the heat pump, but it's really very simple if you think about it. Let's look at the graphic real quick. And we see that in the cooling mode of operation, we're going to take hot gas, kind of follow the graphic. We're going to take hot gas from the compressor in the cooling mode. We're going to go to the outdoor coil, and that outdoor coil is going to condense that hot gas into a liquid. That liquid is going to go past a check valve circuit in the outdoor biflow expansion valve. And that's why we have to have a biflow TXV, is it has to meter refrigerant in one direction, but allow it to flow freely in the other. So in the cooling mode of operation, looks just like an air, excuse me, guys. Oh my goodness, got a little cough there. So in the cooling mode of operation, we've got hot gas from the compressor going through the reversing valve to the outdoor coil, and then down the liquid line and through the biflow filter dryer to the indoor TXV. That indoor TXV will then spray liquid refrigerant into the indoor coil. It'll return back on the vapor line to the reversing valve, loop through it, back on the suction line, back to the compressor. So in the cooling mode of operation, the outdoor coil is going to be warm, the indoor coil is going to be cold in the cooling mode of operation. Heating mode of operation, let's watch the graphic. In the heating mode of operation, we notice hot gas from the compressor will be diverted to the indoor coil in the heating mode. Now remember, team, the indoor coil in the heating mode is actually acting like a condenser. It's going to turn that hot gas back into a liquid as we reject the heat into the home, which is what we want in the heating mode. The liquid line will stay the liquid line. We'll then pass that liquid through the biflow filter dryer. Now the outdoor TXV is going to spray liquid refrigerant into the outdoor coil where it's going to boil off and evaporate. And as we boil that refrigerant off outside, it's going to absorb heat from the outdoor air, and it's going to return that suction vapor back to the reversing valve and back to the compressor. So the big thing about it, go ahead.
We did have another question come in. So the heat pump needs 2 TXVs. Is that correct?
Oh, that's a good question. Yeah, so the heat pump has to have 2 TXVs because remember, both coils could act like an evaporator or a condenser based on what mode we're in. So the indoor coil will have a TXV and the outdoor coil will have a TXV as well. So we're in the heating mode of operation. The outdoor TXV will be operating. That is absolutely correct. Good observation. Good question.
Is there any reason why an AC might have an outdoor TXV?
No, you'd never have you would not have a TXV on an outdoor coil in an AC operation. That's a good question. Good. So really what makes a heat pump is the reversing valve and the fact that we've got 2 TXVs, one for each coil now, depending on what mode of operation we're in. As far as the compressor is concerned, it could care less what mode it's in. It's still just going to be making hot gas and suck gas back on the suction line. So there's no such thing as like a air conditioning compressor and a heat pump compressor. They're just all heat pump quality compressors, and based on the reversing valve and the two TXVs will determine if we have a heat pump or a straight cooling system. Any questions or comments on those ideas?
So Joel, I know we might be getting a little bit more technical here, but there's an additional box that's on the side of the compressor.
Oh, you're talking about the suction accumulator, aren't you?
Yes.
So the suction accumulator, what that's all about, that protects the compressor. But I want everybody to think about this for a second. If it's 25 degrees outside and the outdoor coil is icing up and is pretty cold, you know, we're starting to build ice up on it because it's below freezing and whatnot. What's going to happen when we go into defrost, you can have some liquid slugging back to the compressor from that outdoor coil, especially during defrost. Now, you say to yourself, well, so what? What difference does that make? Well, remember, please remember, compressors are not designed to compress liquid. They're designed to compress vapor only. And so we put that suction accumulator on there as a safety device to ensure that the compressor only gets vapor back to it, because the suction accumulator, what it does, if it sees liquid, if some liquid gets into that suction accumulator, that accumulator will actually boil that liquid off inside that accumulator to ensure the compressor only has suction vapor going back to it. So it's there to protect the compressor and to add additional reliability to our champion product. Good question.
So we got one more comment here. Zach asked, so on an AC application, you'd only have a TXV on the indoor coil?
That is correct. You'd have a TXV on the indoor coil only on an AC only application. That is correct. Good question. Okay. So let's go ahead and open the floor up for a little bit as we think about some final questions or comments on our basic refrigeration cycle. And Emily and Jessica, I'll let you guys again watch the chat box and see what we have for maybe some final questions or comments on our basic refrigeration cycle training we did today.
So at this time, feel free to unmute yourself and let us know if you have any questions, as Joel said. Joel, I appreciate you putting this together. Do you mind putting us back in on the last slide so we can see the cycle again?
The last slide, absolutely.
And since we're still talking basics here, oh, sorry, if you return to the other, is there any difference here? Why we're just showing coils? What's the difference between an air handler and a furnace application?
Well, from a mechanical standpoint, there really is no difference because, quite frankly, a coil is a coil. And so an air handler is going to have a coil built into it already. And a furnace application will have a coil setting on top of it, but the same principles are going to apply. It doesn't matter what that indoor coil physically looks like or how it's configured or packaged up. An air handler will have the indoor coil built inside. The furnace, you'll set one on top of it, but it's the exact same principle. Good question.
What is the reversing valve?
Say again, what was the question?
The reversing valve?
She asked about the reversing valve. So if we go back a couple slides, Joel had a great visual.
So the reversing the reversing valve, this is kind of a graphic right here, but what it does, it's going to divert hot gas. The only thing that reversing valve does, it diverts hot gas from the compressor either to the indoor coil or to the outdoor coil based on the mode of operation we're in. So let me pull that graphic up again. So here's kind of a picture of a reversing valve. You notice there's a single line on top. That's the hot gas line from the compressor. And then there's three lines down below. One goes to the outdoor coil, one goes to the indoor coil, And the middle line of those three are always going to be the compressor suction. So let me pull a little graphic right here, and you can kind of get a better look at that. So what happens in the cooling mode of operation, the reversing valve is going to take hot gas from the compressor and send it outside, and take cool gas from the indoor coil and loop it through back to the compressor on the compressor suction side. In the
So
heating
real
mode,
quick, so Joel, on your last slide, there's a valve that actually can go back and forth horizontally that will switch depending on whether there's a call for heating or cooling.
yes, I like that. Good observation. So inside the reversing valve, there's actually a slide that moves back and forth and side to side. And what it does is it just has some channels machined into it, so that when it's in the cooling mode of operation, it takes hot gas from the compressor and sends it to the outdoor coil, and the cool gas and the cool vapor from the indoor coil, and loops it right back to the compressor suction line. But in the heating mode, it switches internally, it slides internally, and takes hot gas from the compressor and sends it to the indoor coil in the heating mode, which makes sense because in the heating mode, I want to warm the house up, with that hot gas from the refrigeration circuit. So really, if you think about a heat pump and what it's really doing, the heat pump is a very, very unique machine and a very versatile machine, because what it's doing is going to be using the refrigeration cycle for both heating and cooling the home. And frankly, a heat pump is going to be more efficient than just like burning a heat strip, for instance, because we're using that compressor to heat that to make that hot gas. That's a lot more efficient than just like burning a heat strip, or like just like an electric heater. And so that's one of the reasons heat pumps really shine from an efficiency standpoint, because we're using the refrigeration circuit year round to both heat and cool the home. Good questions.
Did that answer your question about the reversing valve? I hope so. We do have some more questions that came in, but Joel, so just as a basic, in an air conditioner application, you're only going to get cooling on the inside. However,
That's
with a
correct.
heat pump, you can get cooling on the inside, as well as you can draw heat from the outside and bring that heat, and so it's going to heat the inside of the home.
That is correct. So the reversing valve allows us to literally reverse the role, or reverse the mode of operation on the two coils. That's what it really does. It allows the indoor coil to become hot in the wintertime for heating, and it allows the indoor coil to become cold in the summertime for cooling. That is correct.
Perfect. All right. So we got another question here. If we go back to the AC section, and if we go back over the sensor on the TXV for an AC application, and how it knows when to spray coolant.
Okay, so as we take a look at that, let me go back and pull that graphic on the expansion valve real quick. So you'll see there's a sensing bulb on the expansion valve. It's just a bulb that clamps onto the suction line of the evaporator. That sensing bulb actually has a refrigerant inside of it. It's probably the same type of refrigerant that the system has in it, but it doesn't have to be. It's a totally sealed system. So that sensing bulb has a refrigerant inside of it, and it's a totally sealed system between that sensing bulb and that little copper tube on top of the diaphragm assembly. So as that suction line warms up, let's say we don't have quite enough refrigerant in there, and the suction line warms up, it's going to warm that sensing bulb up and increase the pressure of the refrigerant inside of that sensing bulb. When it does that, it's going to push on top of that diaphragm, as you see the graphic, and it's going to drive the valve open. Once we put more refrigerant into the evaporator, it's going to start cooling down some as we dump more refrigerant in the evaporator. As we start cooling the evaporator down, that vapor line on the evaporator will also cool down, and the sensing bulb will start cooling down. As we start cooling that sensing bulb down, it's going to ease up on the pressure on top of that diaphragm and allow the valve to close off a little bit. And so that's what happens is the valve will sit here and drift open and drift close based on the temperature of that sensing bulb. Because remember, that sensing bulb has a refrigerant inside there as well, and it's affecting that diaphragm on top, which actually pushes that push rod to open and close the valve. So the expansion valve has the ability to sense the temperature of the vapor line or the suction vapor line at the outlet of the evaporator coil, and then make that valve open or close to maintain an optimal level of refrigerant into that evaporator. And it does it all automatically. Good question.
All right, I hope that helps answer that question. Our next question says, how do we identify the different TXVs? Can we go back to the heat pumps slide? We want to know a standard versus a bi-flow TXV.
Okay, so as we take a look at the heat pump slide, let me pull that up real quick. So the bi-flow TXV, if you were to look at a bi-flow TXV, it looks exactly like any other TXV. However, inside that TXV, there's a check valve circuit. That check valve inside that TXV allows refrigerant to flow freely in one direction, but it meters refrigerant in the other direction. So the reason we call it a bi-flow TXV is because there's a check valve in there that allows the refrigerant. Let's say, for instance, when the let me pull a graphic here. Let's say when the outdoor coil, we're in the cooling mode of operation, and the outdoor coil is warm, and we're in the cooling mode of operation. That bi-flow TXV, the check valve is going to open up so it doesn't restrict the liquid coming out of that warm coil. And so that check valve will open up and allow the liquid to flow freely out of that coil. Now, hang on a second. The bi-flow TXV on the indoor coil, its check valve will be closed, and it's going to force that liquid through the expansion valve circuit and spray it into the indoor coil. So it's important that we understand that the bi-flow TXV has a check valve in it internally. You can't tell by looking at it. It's built in. And that check valve circuit allows the refrigerant to flow freely in one mode and then meter that refrigerant into the cold coil in the other mode of operation. So when you look at a bi-flow TXV, and by the way, any coil or any expansion valve on our residential Champion equipment, they're automatically bi-flow TXVs. So we don't sell just a straight AC TXV. It's a bi-flow TXV that'll work for both AC and heat pumps as well. Good questions.
I'm not sure, did that answer your question, Chris? Is there a way to identify if they were to pick up a TXV out of the shop? Is there a way to tell if it's a bi-flow or a standard?
No, there's not. You can't from the outside. You can't visually tell because it's built inside. That check valve is built inside the body. You'd have to look at the model number of it, and you'd have to look at the the part number of it. But all of our Source One Champion residential expansion valves they're going to be all bi-flow. They're automatically bi-flow, so they'll work in any application. But if you were to go to like a refrigeration supply house and just go buy an expansion valve, you'd have to specify, I want a bi-flow or I want a straight expansion valve, because you can't tell just by looking at it because it's built inside the body. Good question.
The next question that came in, are all JCI heat pump reversing valves energized in cooling mode through O? Just making sure.
I love that question.
Just making sure there aren't any different models energizing and heating.
Okay, so every residential, domestically produced, residential Champion heat pump, everything, commercial and residential, are going to be energizing the reversing valve on the O terminal in the cooling mode of operation. The only exception we currently have in our residential lineup is what we call our HMH7, our new horizontal discharge heat pump, our 1718 SEER heat pump. That's our Hisense product. That is the only product we have in our inventory that's going to energize the reversing valve in the heating mode on the B terminal. So everything is except the Hisense HMH7 horizontal discharge heat pump.
It's a great question.
Good question.
It's getting a little bit more technical, but I think that's great. Great question to bring up.
Good question.
Not seeing any more in the chat. Do we have anyone that has a question?
Yeah, I have a question.
Okay, perfect. Thank you.
So on a heat pump in heating mode, where the outdoor condenser is acting as an indoor evaporative cooler, is it technically going to be operating more efficiently given the increase of surface area?
You know, that's a good question. So without getting into a huge engineering discussion, here's some basics with every refrigeration cycle. The colder the cold coil, or the colder the evaporator, the less capacity that unit's going to have. That's just a general but accurate statement. So the colder the evaporator is, the less capacity you're going to have on a refrigeration system. So to your good point, the outdoor coil, because it's a lot bigger, initially it's going to be more efficient until it starts building ice up. Once it starts building ice up on the outdoor coil in the wintertime, right at the point of defrost, it's going to be the most inefficient at that point. So based on the temperature of the evaporator coil, how much ice you have built up on it, the amount of airflow and all that can affect capacity. But with with a clean coil and it's optimal conditions outside and it's a nice clean coil, it'll be more efficient. Yes, because the size of that outdoor coil is kind of what you're driving at, I think.
So Joel, you're talking about defrost. Can you go into what's going on with defrost?
That's a great question. So basically, a heat pump, because when we're in the heating mode of operation, the outdoor coil becomes the evaporator. It's absorbing heat from the outdoor air and bringing that heat inside the home with the refrigeration circuit like we've discussed. But what's going to happen if you're below what we call dew point, in other words, if we're below the freezing point of water on that coil outside, you're going to start accumulating ice below freezing outside. Once you start accumulating ice on that outdoor coil, we have to get rid of that ice. And so what we do, we sense when that coil needs to be defrosted, with some coil sensors and ambient sensors. And when that coil needs to be defrosted, the heat pump, a couple things happen. Number one, the outdoor fan shuts off during defrost. Number two, it switches into the air conditioning mode to make the outdoor coil the warm coil again in the air conditioning mode. But because we don't want to freeze the homeowner out by putting it in the air conditioning mode, we're going to go ahead and bring on the auxiliary heat inside. So we have warm air going across that coil inside as well, so we don't freeze the homeowner out during defrost. So the big thing with the heat pump and defrost, it goes into air conditioning mode. We shut off the outdoor fan and we bring on auxiliary heat so we don't lose our comfort inside. But and then once we defrost it, we get all the ice off the outdoor coil, and the outdoor coil temperature sensor senses that. It'll then switch it back into the heat pump mode of operation until the thermostat is satisfied.
Perfect. We've got a couple more questions. Is a reversing valve considered a TXV valve?
It is not. Absolutely no. It's a totally different device. It's what is the reversing valve? The sole purpose of the reversing valve is to divert hot gas from the compressor either to the indoor coil in the heating mode or to the outdoor coil in the cooling mode. That's the sole function of the reversing valve, is to divert hot gas from the compressor to either coil, depending on what mode of operation you're in. Good question.
Yep, perfect. So you can see on the graph here, the reversing valve looks a little bit different. They're both considered valves, but a reversing valve is a little bit different. And then the TXV, you can see down at the bottom, there are two different different valves. So great question. Next one on filter dryers, better at indoor coil or as built into the condenser?
You know, that's always kind of a field debate that I hear quite a bit of. The fact about it is it makes no difference. We happen to put them on the outdoor in the outdoor unit. We factory install them, and it's just one less thing for the contractor to do. But from a practical standpoint, anywhere in that liquid line that's convenient for installation. Here's very, very important point though. Make a note of this. Put this in your back pocket. Write this down. Whatever you put a smiley face so you don't forget it. We only want one filter dryer in a liquid line. We don't want to have multiple dryers in the line because if you do, you're just asking for a liquid circuit restriction. So make sure that if you install a filter dryer, you know, in the liquid line, wherever the contractor likes to put it, whether it's inside or outside, make sure that there's not one on the cabinet outside, because you don't want two filter dryers back to back because you're asking for a liquid circuit restriction. But as far as you know, just normally installing a filter dryer, it doesn't really matter where you put it in the liquid line. It's mostly for the convenience of the installer as to where you put it.
It's a great point, Joel. Thank you for that question, Greg. Do we have any other
Absolutely.
questions? On the compressor, okay, on a compressor change, I believe it should be out, change out. Yep, change out. Should they cut the factory installed filter dryer and put a new one?
Absolutely. Yes. So anytime you have a compressor change out, and really I recommend anytime you open the refrigeration circuit, if you have to open the refrigeration circuit for service, go ahead and change that filter dryer out. Now this is really, really important. If the factory filter dryer is in the cabinet outside and it's hard to get to, go ahead and cut it out and just pipe it straight through with a straight piece of pipe, and then just put that filter dryer anywhere in the liquid line that's convenient for you. So the main thing is if you do a compressor change out or you open the refrigeration circuit, get that old factory dryer out, but you don't have to put the new dryer in the exact same place. If it's not convenient to do so, you can just pipe it straight through with, you know, just braze the pipe together inside the cabinet, and then put that filter dryer anywhere you want in that liquid line that's convenient. It will not affect the warranty in any way to do so.
So I know we're getting a little bit more into the components, but why would we have a filter dryer, Joel?
The filter dryer, what it's going to do, it's going to absorb any moisture that might be in the system. You know, sometimes installers get a little bit lazy as far as putting it on a vacuum pump to evacuate it and to get all the moisture out of the system. And so a filter dryer protects the expansion valve in the system from moisture because it absorbs moisture. It's a very, very powerful desiccant. In addition, it filters the refrigerant. It, you know, mechanically filters the refrigerant with a very, very fine screen in there as well to protect the expansion valves from debris and whatnot that may occur during installation. So the filter dryer is just good insurance to have a nice, clean, dry system.
That's great. We've got one more question here, Joel. TXV installation instructions mention indoor use. Do heat pumps come with a different factory installed TXV?
You know, that's a great question, you know, and based on the age of the product and the SEER rating of the product, you could have a different TXV. You'll have different TXVs for different functions. But great news, you ready for this? Our new coil platform, our new coils, our new X series of coils, there's only going to be 2 expansion valves for both heating and cooling. I should say for both AC and heat pump application. And those coils are going to just feature 2 expansion valves across the entire tonnage. So in the old days, we had several based on the application, whether it's heating or heat pump or straight cooling or, you know, and whatnot. But now we're down to 2 expansion valves with our new coil lineup. So that's the great news on that.
That's great. So the heat pump already has one installed in it, but when we install for, we typically have to install it in the indoor coil, or it might be factory installed on the indoor coil, correct?
That is correct. It's going to be depending on how it's ordered. But also, please remember, all of our expansion valves on our indoor coils are bolt-in. So it's just a simple matter of bolting it in. If you don't have one factory installed, you just bolt it in at just a couple of crescent wrenches, and you put a drop of oil or so on the thread, so it goes on smoothly, and then field installed, it's no big deal. Just a couple crescent wrenches is all you need to do that. Good questions. Any other good questions or comments that we could talk about today?
All right, Joel, I got another one here. What's your opinion on introducing leak stop and or UV leak detection dye?
I personally do not like it because you're putting something in the system that's foreign. I know some contractors have used it successfully. I don't think any of the manufacturers, us included, I don't think we void any warranties or anything like that. But I like a good electronic leak detector, and good brazing practice and good good refrigeration practice seems to work better. As a last ditch effort, if you just can't find a leak, maybe in a coil pack or something like that, it might be beneficial to use it, but I typically don't like it. I just like the older methods of electronic leak detector, visual, soap bubbles and stuff like that have seemed to work well for me over my short career.
And as Joel was saying, it is not exactly short. That was definitely a sarcastic comment there.
Oh my goodness. Yeah, I was actually teasing everybody a little bit there. I graduated technical school in the spring of 1974, so everybody can kind of do the math.
Yes, we definitely have got a valued asset for Joel as our training and tech guru. So, all right. Did I miss any other questions in the chat? I think we've caught all of those. Any other questions that we want to speak audibly?
Emily, do you want to put the next series into the chat?
Oh, I was going to have that on hand and I didn't get that yet. But yes, great point, Jess. I definitely wanted to do that.
So just to give everybody a little commercial, Emily, we're planning on our next training session as being the compressor story. We're going to talk about compressors and the different types of designs and why we use a particular design in our platforms and tonnages and stuff like that. So please join us for the next go round with our compressor story for our next training session.
That's right. So now you guys should be able to see in the chat, we do have the June 23rd at 1 p.m. Central Time. We're looking forward to talking about compressors in a little bit more depth. And if you guys have any feedback, we'd love to hear from you guys on any type of training. Joel has a great training class that he has, as well as the YouTube channel for his trainings. But we definitely love to hear you guys' feedback as we continue to do this HVAC basic series. We are planning to we're planning to kind of continue with the basics, and we will eventually do more of, as we continue to build our story, we will do some in-person and kind of put it all together. So looking forward to working with you guys as we continue.
Fantastic.
Great job, Joel and Emily.
Well, thank you very much. Any final questions or comments? And if not, we'll go ahead and secure for the day.
All right. Yeah, definitely check out. We've got the YouTube playlist that Jess has in the comments, as well as click on the comments where you can register for the compressor story coming up June 23rd.
I was muted. I did have a comment, question. Can you still hear me?
Yes,
we can.
Absolutely.
This is Bill with ERC in Loveland. Part of the reason we attended this webinar is because Gerald at Longmont Wind Air said that Joel is a great resource to have in case you want to contact him with any troubleshooting questions. So Joel,
Yes.
Is that true? Do you mind people contacting you? And if not, what's your phone number?
No, please call me anytime I can lend a hand. My number is, please write this down, everyone, 251 area code
Say again.
510-8563.
You were breaking up, Joel. Can you repeat the number?
Absolutely. 251 area code,
Okay,
510-8563.
okay. Got it. Thank you.
You bet. Please call me if I can lend a hand.
Yeah, I think they said Longmont, right, Joel? So Chris Fannin taught you everything you know.
I would tell you what, they don't get much better than Chris Fannin. He's top notch.
So June 23rd Central Time, we've got 1 o'clock Central Time. So Eastern Time, that would be at 2 Eastern, if I'm doing my math right.
That is correct, Emily.
So in Longmont, that will be at noon.
Yep.
So, and yeah, feel free to kind of give us any feedback. We kind of tried to select. We've got a national base with wind supply, so we definitely been trying to keep it at the best time as we can, but it seems to be kind of noon to afternoon seems to be our best time. But if you have any other times you would like, please feel free to let us know.
Okay. Well, thank you everyone for the opportunity to train with you today. I hope you enjoyed it, and we look forward to doing it again with you soon.
Thank you.
You bet.
All right, thank you guys.
Have a good afternoon.
Bye-bye.